Derive expression for volume flow rate Q of the oil between the two plates. Yeah, it's a little weird to understand. So my meaning, I may be wrong, is that we have to find the fluid velocity flowing across the two plates. Will that ring a bell? So imagine we have a fluid, okay, the volume of fluid. This is the volume of fluid moving across the two plates. Okay, so this is one plate and this is the two plate. So we're trying to find the fluid velocity moving across these two plates. Okay, so the reason, so how does this fluid move is mainly to the torque power generated by the shaft, okay, generated by the shaft that is spinning, and the bearing itself. If the bearing itself has lesser friction coefficient, the flow will flow faster. If it is more resistive, the friction, it will actually flow slower. So this is just the meaning. So you're just simplifying, trying to find the volume flow rate. You may ask me, why do I find this? What is the difference between volume flow rate and the velocity, which we found earlier? This is the velocity component u, where it's just the particle itself, I believe. Okay, we're talking about the particle moving in the horizontal velocity component u. Well, now we are talking about the whole. We're talking about everything. We're talking about a family of particles moving across it, and across the whole spectrum. So the plate itself, as you can see, this is the shaft. This is the one that has velocity u, that is turning. Okay, and then the fluid is the the fluid. There's one particle over here, another particle, another particle, another particle. There's many particles that follows this velocity profile, right? So it's determined by the y, right? So the velocity, so the particle, so a lot of particles fill up this whole y, and therefore we're trying to find an average volume flow rate. Okay, so the typical u is actually to find, is just a particle velocity, that's all. And then this one is actually to find the volume throughout the whole system. So without further ado, we actually solve. It's pretty straightforward. So what you need to do is actually to put y equals to 0, which at this point, this particle at this 0 point, and integrate across many particles to this y equals to a. And taken from the u, okay, what we derived very earlier in the previous videos, our u is actually this formula, right? The velocity of the particle is actually this u. So if I were to copy and I paste, see, it's exactly the same. So I didn't cheat a filling. Okay, they're the same. Y over 2 nu. Okay, and then I integrate them. So when I integrate uy over a, you have uy square over 2a plus del p del x, the same, it stays constant throughout, and then y over 2 nu. Y over 2 nu, you multiply y, you have y square. So y square over 2 nu, if you integrate, you have y cubed 6 nu, right? So this is where it is. And then minus, so now it's y over ya. So this, just now is this times this, now it's this times this. So this is ya. You integrate one time, you have y square, ay square, and then 4 nu. So this is what it is. And then plus c, so then constant, and then the definite integral y equals to 0 to y equals to a. And then you can straight away cancel. So when y is equals to 0, okay, hold on a while. Okay, so when y is equals to a, okay, I just sub in the a's. So this y I'll just sub in into a, and then this y I'll just sub in into a also, and then this y I'll sub in into a. So all the y's I sub as a, and then when I sub in y equals to 0, okay, y equals to 0, this whole thing becomes 0. And y equals to 0, this whole thing becomes 0. And y equals to 0, this whole thing becomes 0. So 0 minus 0. So this whole expression becomes 0 when you sub in y equals to 0, which is over here. Right? So now we are talking about only y equals to a. Because when you sub in y equals to 0, everything is 0. So what I need to do now is to rearrange a little. So how do I rearrange? So UA, okay, this is denominator A, so I can cancel away. So I have UA over 2, okay, and then W dx is the same, and A cubed over 6 nu minus A cubed over 4 nu. What I need to do is actually to multiply by 4. So this is 4, 24, and then 6, 24. So I just try to make the denominator the same. So 4 minus 6, you have minus 2a, right? This is this one over here. And then and then I cancel away this. Okay, so I have minus 1 over 12 a cubed over nu. So this is what it is, a cubed over 12 nu, right? So this is, so I just bring this negative out over here. So I have my equation to calculate the volume flow rate. So just to recap, just let you know that the volume flow rate talks about all of the particles that is moving across. Okay, while this U equation that we derive using the Navier-Stokes equation, okay, which is this one, Navier-Stokes equation we derive all the way until here, is actually to describe the velocity of the particle itself. That's all. Nothing much, nothing fancy. So I hope I didn't confuse you throughout the way. So I'll see you in the next video to talk about this part. Okay, this is the pipe flow. Just now we talk about, okay, next video I'll talk about it. So see you.